Welcome back. In this chapter 8.1.2, we'll introduce the Argand diagram, which allow us to represent complex numbers geometrically in the complex plane. We'll also introduce what is the polar form of a complex numbers, as well as what the unit circle is, a term commonly used in complex numbers literature. We have this line along the horizontal axis, and we call this the real number line. In the middle, we have the origin, and as the number grows larger positively, the numbers are positioned more and more towards the right hand side till infinity, positive infinity. And of course, numbers growing more and more towards negative values, it moves along the left towards negative infinity. And this line is the real number line. Now, if this is the real number line, where is the imaginary number line? It is the line perpendicular to the real number line. It also has the origin sitting at the middle. So as the imaginary number grows more and more positive, then we have actually the imaginary number growing larger and larger upwards in this upward fashion. So we have 1j here, 2j, 3j, and 4j, and so on, growing larger and larger, growing more and more positive values. And when it grows more and more negative value, this is minus 1j, minus 2j, and so on. And again, it also grows towards negative infinity. So you can also visualize these two axes as positive real axis and imaginary axis, and it allows us then to visualize the complex numbers on a plane. So now let's see some examples of imaginary numbers on this plane. This is 6 plus j, 4. What it means is that you move along the real axis by 6 units and 4 units upwards because it's plus j4. So this point is 6 plus j4. What about 5 minus j6? Similarly, because it's positive 5, you move along the real axis by 5 units, and then because it's minus j6, you move downwards along the vertical axis by 6 units. So this is 5 minus j6. Let's have one more example. Minus 7 plus j6 means you move along the real axis by 7 units towards the left because it's minus 7, and positive 6 upwards by 6 units. So these are 3 examples of the complex numbers on the complex plane. We now continue to introduce some notations that is convenient for us when we want to represent complex numbers on the complex plane. This z equals to a plus jb is the complex numbers represented as in the rectangular form. We have another form which is called the polar form. To represent complex numbers in the polar form, we need the magnitude and the angle. Okay, so where's the magnitude and angle? Well, let's have this complex number a plus jb. Basically, it means move a along the real axis and move b along the complex axis. Now, to get the same point, we can represent this as z is equals to magnitude of c, angle theta. What are we talking about? Well, basically it says that we're going to have complex numbers that have the magnitude. Magnitude here means the length, with length this value, and with angle theta. So how to calculate the magnitude? Well, this is a right angle triangle, and by Pythagoras theorem we know that this length, the hypotenuse, is square root of a square plus b square. So this is the modulus of the complex numbers. What about theta? Theta is the angle that is made with respect to the positive real axis. So we take the positive real axis, and if the angle of this line is made anti-clockwise, then by convention we call this the positive angle. And if angle moves clockwise, then this is negative angle. Okay, we call this the argument of z to denote the angle theta. Angle theta is tangent theta equals to b over a because it's opposite over the adjacent. Tangent theta is b over a. So we can calculate theta by using arctangent, implying theta equals to arctangent of b over a. Now theta is measured with respect to the positive real axis, and theta we restrict to less or equals to pi greater than minus pi. Okay, and theta is typically measured in radians and not in degree in our course.